So when we're using dynamical systems models to ask sustainability questions or questions relating to sustainability science, then the long run behavior of the systems is really important. So we really care about what the systems do kind of at steady state. Now, in these simulation models, when you set a parameter and you hit play, you get some interesting trajectories out. You might get some interesting transients, so things that happen initially but then fade away over time. But then ultimately, when we really ask, is this a sustainable solution, we're not necessarily focusing on those transients. We oftentimes are focusing just on kind of the right-hand side of the trajectories. Does this result in something that can allow for future activity for a sustained period of time? And so with that, we really often are asked to summarize what is the relationship between a parameter and how something behaves in the long run, not the short run. And so having to generate a lot of trajectories for every single parameter that you might think of, and then show that across these trajectories you get some outcomes that are sustainable and some outcomes that aren't. It seems like there should be a more concise way to present that information, maybe getting rid of all the transient data and only focusing on the possible outcomes that we would see in the long run as things kind of settle down. And so today I am going to present what's known as a bifurcation diagram, which is a diagram which does exactly that, and it is commonly used in the dynamical systems community, not just in simulation, but also in the people who are sort of more focused on strict mathematical models. But generally, any dynamical systems model that you can discuss in terms of the outcomes that persist over long periods of time, you can use a bifurcation diagram to summarize. So let's look into what one of these bifurcation diagrams looks like. And I am going to be using a fisheries model as the kind of motivating model for this, but this can apply to lots of other models as well. All right, so let's get me out of the way. All right, so a bifurcation diagram. Roughly speaking, a bifurcation diagram is a graphical depiction of how possible steady state outcomes change with some important parameter. And I say possible because some parameters may have corresponding with them multiple possible outcomes that can happen in the long run, and we need to somehow capture all of those all at once. So let's just as a reminder what we mean by some of these terms. So by important parameter, well, let's see, what is a parameter? In a simulation model, or really any model, a parameter is a variable that we don't actually think of as varying. In other words, it's constant with respect to our time scale of interest. And so it is something that can be changed by you when you run the simulation, but inside the simulation, as far as the simulation is concerned, it's constant. And so that's what we mean by a parameter. It is relatively constant compared to the other dynamical variables. And so dynamical variables, those are the ones that are actually changing on the time scale of the simulation without you doing anything. You hit run and they immediately start changing, and they could change over long periods of time, or they could settle down and become constant. So they can become constant, but the whole idea is that they have the ability to change, whereas a parameter with respect to the simulation should never change unless you actually manually go in and change it by hand as the human operator of the simulation. So a bifurcation diagram is designed so that it will only show the steady state, so the sort of the long run behaviors of the dynamical variables for each parameter choice. And so we've got parameter choices on the x-axis, and we've got the steady state values on the y-axis, so the things that can happen over long periods of time. So I've got, instead of using this fisheries model, so I've got harvest rate as my parameter, and I've got fish population as my dynamical variable that I'm interested in the relationship between the steady state fish population and each individual value that I could set for a harvest rate. So how do I generate this thing? Well, if I look at the so if I think about a logistic growth model for a fishery, then I get a plot that looks like this. Now, this also could apply to lots of other natural renewable processes that act like fisheries. So generally, anything where I need to maintain a certain stock in order to guarantee future growth that I can harvest, I could apply this same type of model too. We just use fisheries because they're kind of an easy thing to wrap our heads around. But I mean, the basic idea is that anything that has a maximum sustainable yield, where a maximum sustainable yield is sort of a maximum amount you can take away from a renewable resource before it becomes a non-renewable resource. And so we think of a fishery as a renewable resource because we can fish from it, and then the fish will naturally reproduce, and that allows us to continue fishing from it for as long as we want. That's what makes it, sustainable. Now, if we overfish from a fishery, then now it's like borrowing from the principal at the bank instead of just the interest, or taking away from your principal in your savings account. Once you start overfishing, going above the maximum sustainable yield, then the fish won't be able to reproduce fast enough to deal with the harvest rate, and you're just going to get a decline in the population until there are no fish left. So that's not a sustainable outcome. And you can think of lots of other renewable crops that act that way. And once you go over the maximum sustainable yield, it's almost like the fishery becomes an oil well, and you have to manage it in a very different way. But so that's the type of system we're analyzing here. I'm going to talk about fisheries, but this could generalize. So the idea is, for every harvest rate, that's what we see down here, if I look at my net regeneration curve, which is implemented as a lookup table in this particular model, then I see that there are two densities that perfectly balance that harvest rate. In other words, at both this low density and this high density, the fish produce exactly the right amount of fish per year to balance the desired harvest rate, so that the fish population will stay constant. So if I start at either one of these, at this low one here, then I will stay there forever. Now, there is a critical difference between these two. So at this low value, I'll call it an equilibrium value. So both of these are potential equilibrium values. In other words, if you stay exactly at that value, you can stay there forever, and the system stays in balance. It stays at equilibrium. But there is something special about this equilibrium down here. If I add just one more fish to the population, that one more fish will have the ability to reproduce, and I now will reproduce at slightly higher than the harvest rate. So if my regeneration rate is slightly higher than the harvest rate, then that means that I will rush away from this equilibrium. I will end up getting a greater density of fish, which will generate a higher regeneration rate, which will be even higher than the current harvest rate, which will mean further growth in the density, which will mean a further increase in the regeneration rate, until I finally hit this special point where the regeneration rate starts decreasing again, and then I'm finally back to this this higher equilibrium value that keeps everything in balance. And so adding one more fish kind of breaks this equilibrium, so that then the population rushes away to this other equilibrium value. Similarly, if I take one fish away at this equilibrium value, then suddenly the fish population won't be able to keep up with the catch rate. And so it will start declining. So the density in the fish population will start decreasing. And as the density decreases, the regeneration rate will decrease, which will create a further gap between the regeneration rate and the harvest rate. And that will then cause further population declines until you reach this point down here. So there's another sort of implicit hidden equilibrium, and that equilibrium is the no fish equilibrium. So if you start with no fish, it doesn't matter what harvest rate you want. You're not going to get anything out of the fish population, and the fish population is going to stay at zero. And if you try to harvest at that rate, then you're going to, any fish that are produced, you immediately harvest, and they'll go right back down to zero. So we've got this middle equilibrium. And if we pop out and start thinking about a similar analysis for this upper equilibrium, if I'm sitting at this higher density or this higher population, if I add one fish due to high competition for food among the fish, then each individual fish will have a harder time finding food, and the regeneration rate will actually decline. That will end up being a lower regeneration rate than the harvest rate, which will cause the slightly larger fish population to then decline back down to its original levels where they were in balance with the harvest rate. Similarly, if I were to take one more fish away so that the density was now less than this equilibrium, then that will end up causing the regeneration rate to jump higher than the harvest rate. And that will mean I will get growth in the population, and so the density will return to the old density here at this equilibrium. So this equilibrium always comes back to itself after small perturbations, while the other equilibrium that we just saw rushes away. Now we should probably do the same analysis for this no fish equilibrium. If I add just one fish in the no fish equilibrium while I'm trying to harvest at this higher rate, that one fish will get gobbled up almost immediately. Even if it can produce a few offspring, that one fish and its few offspring will also get gobbled up almost immediately, and then I'll have no fish again. So the no fish solution is also a stable equilibrium. So we've got these three equilibria, one of them which is kind of just sits there and it needs to be very, very perfectly balanced in order to stay there. And if you add or subtract one or a fish in either direction, it'll rush towards the other equilibria. Sorry about that. The other equilibria, which are on the top end and the bottom end here. You can kind of liken this, these two cases, to if you had a pencil that you had balanced on the tip vertically. So if the pencil is balanced straight up and down vertically, and you get it just right in the center, it might be able to stay balanced like that, but if you just happen to bump it a little bit, it's going to fall over on its side. And so the pencil being, it technically could stay upright forever, but it's sort of not a safe equilibrium, because with just a slight nudge in either direction, it will fall over. Now when the pencil's on its side, we can be pretty confident that it's going to stay on its side forever. And so somehow this, even though it can balance here, this balance point is unstable and this balance point is stable. And so those are actually the terms that we use in the dynamical systems literature. We call those two outer equilibria stable equilibria. And when you have two stable equilibria, you're pretty much always going to find that there will be an unstable equilibrium in between them. This is kind of like if you have two valleys, you almost always have to have a hill in between them. And so in order to separate the two valleys. And so that's what's going on here. So we have three possible equilibria that can come out. So three possible steady state values that can come out of this one harvest rate. So what we're going to do is try to build a diagram where we catalog all of the equilibria for each harvest rate. So for this one harvest rate, we've cataloged this one, and this one. And you can see that if we just take this net regeneration lookup table and flip it around so that, this was in fish density, but if I scale fish density, I can get fish population. And then net regeneration rates on the x-axis, but, so I just turn that into harvest rate. And so by flipping this thing around, I end up getting this curve here, which looks very similar, and that curve will end up being the one that allows me to then etch out for every harvest rate what are all the possible equilibria. And so I'll always have the no fish equilibria, and then I'll have this unstable equilibria, which corresponds to this portion of the graph, and then I'll have this stable equilibria, which corresponds to that portion of the graph. And so this is what a typical bifurcation diagram looks like. You end up getting solid lines and broken lines, where the solid lines depict stable equilibria, the broken lines are unstable, and then, again, solid lines stable. So for every harvest rate, it's very clear that if I pick a particular harvest rate in this region on the left-hand side, I get 3 equilibria out, stable, unstable, stable. But if I choose a harvest rate on the right-hand side, then I only get 1 equilibria out, the no fish equilibria, and it is stable. So let's, you can kind of think about, well, when I look at this plot, what does this tell me about where things will go in the long run for different initial conditions? Well, if I am at a harvest rate that's on the left-hand side of the plot here, so long as my initial fish population at that harvest rate is under this curve, which corresponds to being inside this curve here, then I will get growth, and the fish population will climb up to a steady state value that is non-zero. If I also have a fish population that's sort of at its carrying capacity, so it's very, it's up here at high, it will then decline, but then it won't decline all the way to 0. It'll decline and stop here at whatever stable equilibrium corresponds to that particular harvest rate. Now, if for any particular harvest rate I'm outside of that special region up here, then I'm going to decline to the other stable equilibria, which is that no fish equilibria. So if I am at a way higher harvest rate than I could ever sustain, I will then just deplete the fishery of all of its fish. But even at some harvest rates, which are sometimes sustainable, if I don't start with enough fish, then those harvest rates will also end up leading not to a stable situation, or not to a sustainable situation up here. It'll lead to the no fish equilibrium. So I get these 2 regions, this blue sustainable region, which is the combination of harvest rates and initial fish populations that we consider to be sustainable because they lead to long-run outcomes which still have fish left in the fishery. And then I have this red region where if I start in the red region, so if I combine a harvest rate with a fish population that's in the red region, then I'm guaranteed that if I don't make major changes, then in the long term, I'm going to deplete the fishery of all its fish. The region in between the two is known as a tipping point for reasons that we'll describe in a few slides here. But typically when we have these bifurcation diagrams where you get these solid regions where there is a particular point in parameter, if there's a special value of the parameter that causes the number of equilibria to change, so I went from 3 equilibria to 1 equilibria, then that usually indicates that we have a tipping point in the system. And again, I'll get to why we call it a tipping point here in a second, but let's get a little more intuition about what it was going on in these systems. So imagine if you started at this smiley face here, which is a particular harvest rate, whatever this harvest rate is, and a particular fish population, say 80% or whatever this is, 66% of the carrying capacity. And someone decides to then increase the harvest rate. So we start here, and then we increase the harvest rate to some region which is way higher than the fish can ever regenerate. So we are in the unstable region for sure. So we are asking for 800 fish per year, but we know that the fishery can never provide any more than 550 fish per year. And so that's going to mean that while we're up here at this high harvest rate, then we are going to see declines in the fish population. And if we somehow have measurements which allow us to tell that we see these massive declines in the fish population, we might then go back to our old harvest rate. And that is because we're hoping that we started out with that harvest rate and we were fine. So maybe if we just go back to that old harvest rate, we'll still be fine. But because the fish population has gotten smaller, then even though we've declined to a harvest rate which used to be a good harvest rate, it is now not a sustainable harvest rate because we don't have enough fish to sustain that harvest rate. And so we see further declines in the fish population, which will mean that we need even further declines in the harvest rate in order to finally bring us back into the blue area where we hardly are harvesting anything whatsoever, but at least the fish now are in a point where they can start regenerating and growing again, and they will grow to near carrying capacity. And once they're there, we can now increase our harvest rate again, and we increase our harvest rate back to the harvest rate we started at, and then that will then bring the fish back to that equilibrium population. So one harvest rate, simply knowing the harvest rate isn't enough to knowing whether that is a sustainable outcome, that will lead to a sustainable outcome. The history of the system matters. And so we end up getting this behavior where if we start at this initial condition here, and we make a relatively small change in the harvest rate, due to the dynamical features of the system, in order for us to get back into the sustainable region, we need a very large change in the harvest rate to get back to sustainability. So a small change got us out of the sustainable region, and we now need a large change to get us back in the sustainable region due to this dependence on the history of the system. And that is something called hysteresis. And hysteresis is often associated with these tipping point behaviors. And hysteresis is a fancy name for when the relationship between a parameter and the state of the system depends on the history of the system. If somebody asks you, is it sustainable to harvest this fishery at 300 fish per year, you can't tell them if it's sustainable or not without them then telling you exactly how many fish are currently in the fishery. So I can't give you a rule that says it's always okay to harvest at 300 fish per year. It really depends on, well, if there's 5 fish in the fishery right now, then there's no way that's sustainable. But if there's 600 fish in the fishery right now, then that will end up being sustainable. And so, so effectively, the decisions about the harvest rate, which will be decisions about how much fish are left in the fishery, are going to affect which harvest rates are sustainable. So that term hysteresis is one that you'll see a lot in these systems. And the term hysteresis loop is this pattern where you get a small perturbation, causes a major change in the system, and then requires a very large perturbation to get the system to switch back. So, now that we've seen bifurcation diagrams and hysteresis, let me close with sort of trying to give some more intuition as to why we're even calling these things tipping points. And I'm going to use an analogy with a refrigerator, sort of basically a large, heavy, rectangular object, in order to sort of understand what we mean by this. All right, so let's think about this refrigerator, and it's sitting on level ground. So we've got a refrigerator sitting on level ground. If you slightly push on the refrigerator, it might wobble a little bit, but it will stay upright. So it has the ability to stabilize itself after a small perturbation. Now, if for whatever reason, maybe you're moving it into the garage and the only place you have to place it is on a slight incline, then the refrigerator will still stay upright. But if you push it a little bit, you might be a little more careful because you're afraid it might tip over. But as long as you push it a little bit, even because the angle is so slight, it's still going to level itself and stay roughly upright and still be usable as a refrigerator. So it will quickly return to that position. Now, the problem will be what happens when it's tipped so far that its center of gravity is right over top of one of its supports. So in that particular case, then you really better not nudge it, because if you nudged it, it's going to fall over. And when it falls over, it's going to be in a very, very different state than it was before. So it didn't have the ability to save itself, and as a result, it ends up landing in a totally different position, an unusable position for a refrigerator. Now, thinking as you might think in the case of a fishery, maybe we can just restore this parameter to a previously sustainable parameter. So if we make this flat again, so we've now restored the refrigerator to level ground, then we might think that suddenly that will fix the problem, because at once upon a time when it was level, then the refrigerator was usable. But that wasn't enough to bring the refrigerator back into its old position. It is still unusable in this position. And so the only way that it's now stable in this new position. If you perturb it a little bit, it'll actually stay in this wrong position. So the only way to get it back into the right position is to actually tilt it at an angle far in the other direction, far more than it's ever been in before, and that will finally allow it to right itself, bringing it back into the old position where it's usable. And so that's what we mean. We've got these two regimes of behavior where the refrigerator is either in a usable state, upright, or an unusable state on its side, like the pencil on its side. And the angle that separates these two regions is the tipping point. And so it is the angle of this parameter, where the parameter is the incline you install the refrigerator at, that is just before the position where the refrigerator is going to tip over, so that if you accidentally bump on the refrigerator, it can then switch into that other mode and won't be able to come back unless you tilt it the other way. Now, the term tipping point actually came from physicists thinking about champagne glasses that are shaped a little bit like this. And if you think about a glass holding a liquid, once it tips over, that liquid spills out. And even if you can right the glass, the liquid doesn't ever go back into the glass. And so very often these tipping points are associated with irreversibility. So in the fishery case, we at least had a path where if we brought the number of ships that are currently fishing the fishery back down to a sufficiently low value, the fishery could grow again. And with that growth, then you could get back into the state of the fishery that it was previously in. But you can't do that with a wine glass. And there are other dynamical systems that are kind of like the wine glass, and they're often associated with things like climate change. So here's sort of a diagram that I borrowed that lists a bunch of dynamical systems related to climate change. So you can model each one of these kind of oval-shaped areas or with a dynamical system that has a tipping point. And in this particular diagram, the authors of this diagram are suggesting that certain ones of these dynamical systems have already tipped. So they are already in the sort of refrigerator flipped over view, and it may be impossible to tip them back. So if you think about Arctic sea ice, there are natural restorative things that will bring sea ice back, but once you tip to a particular and you get runaway melting, then the sea ice isn't going to put itself back unless you take the Earth and cool it down to far cooler than it has been, and until you can bring the sea ice back into that area where it can naturally restore itself. And so these Arctic sea ice and the Western Antarctic ice sheet are both listed as tipped here, and then a bunch of these other ones, potentially could be, near their tipping point. And so there is a major sort of area of research to try to take statistics from these systems and determine if they're getting closer and closer to their tipping point. So there's this thing called critical slowing down. You can watch how quickly something restores itself. Like when you nudge that refrigerator, you can see how quickly it ends up settling itself back up. And if it kind of wobbles for a large amount of time, then it might be near one of these, tipping points and be really at risk of tipping over that tipping point. But if it settles itself very quickly, then maybe it's far from it and there's a big buffer. So we often talk about tipping points when we talk about climate change, but as summarized by popular literature, like this very popular book by Malcolm Gladwell, there's a lot of other ways in which you can see tipping points. You can imagine political instability. Imagine a group of civilians governed by a government, and that government does something which upsets those civilians. They might start a revolt. Now, in order to ameliorate the revolt, to bring everyone back in line, the government might give people back something that they took away. But once the revolt has started, once the revolution has started, simply giving people back that which they've taken away may not be enough to stop the revolution. You may have to give them a lot more to stop the revolution, or it might be totally irreversible. So you can come up with models of political instability that look like these tipping point models. There also can be good tipping points, and so you can imagine that people might be latched into a sort of negative behavior, but if you just get, you put enough effort into changing their behavior, then eventually, once there's a social norm, word of mouth that ends up stabilizing the good behavior, then you may not need to be so heavy-handed. You can actually reduce the amount of effort. So, for example, you might give people tax incentives to start installing solar panels on their houses. So you have to provide the tax incentives to get them installed. But once they're installed, because there's economies of scale, then maybe it actually becomes cheaper to install those solar panels and so on and so forth. And so eventually you don't need the tax incentives to get people to install those solar panels. They end up installing them on their own. And so the system has tipped, and you can actually reduce the parameter so that you don't provide any incentives, and you might even be able to start taxing them even for using the solar panels. Now that might cause the system to tip back, but I hope you see what I'm saying along these lines. And you could probably come up with lots of other examples. So, the reason why Malcolm Gladwell sort of made so much money off this book, The Tipping Point, is that I think once people are sort of familiar with this idea of tipping points, then they start seeing them everywhere and realizing just how interesting and terrifying these things are. But the big thing I want you to take from these slides here is that when you hear people talking about tipping points, there's a colloquial definition of tipping points, but when we as sustainability scientists and dynamical systems theorists talk about tipping points, we have something very specific in mind. So we are referring not just to changes in systems, but we are referring to this interesting relationship between the parameters and the long-term outcomes of systems, so that when a system has a parameter which has gone so far that it causes a system to switch into a different mode, where if you move that parameter back to a previous value, the system doesn't behave like it previously did. So that's the tipping point. That's the refrigerator being tipped over on its side. It is specifically a parameter, a critical value of a parameter, where it almost is like you flipped from one simulation mode into a totally different simulation mode. It's like I started one simulation, I moved my parameter, and I started a different simulation without realizing it. And so when I moved the parameter back, my system didn't behave like it used to in the old simulation. But the sort of interesting thing about this is it still is all one big simulation. It's just acting different because now the history of this parameter change actually matters. So that's what we mean by tipping points. I hope that's helpful, and I hope the bifurcation diagrams make some sense.